Nuclear chemistry, reactions of the nucleus. If you will think back to when we started talking about atoms, we discussed how protons and neutrons are the only particles located inside of the nucleus. So if you'll kind of zoom into the nucleus with me for this week, we are just going to be focusing on those two particles in these types of reactions. And we call them nuclear reactions because they're occurring in the nucleus. So our first definition here, nuclear reaction, is a reaction in the nucleus, which means it involves protons and neutrons. No electrons are involved in nuclear reactions. And you'll notice as we go through all of our study of chemistry, the goal in a reaction is always to become more stable. So our nucleus is going to be trying to become stable. And the way that a nucleus becomes stable is to be small enough. They're unstable when they're way too big, too many protons or too many electrons. And so what will happen is these nuclei will go through reactions to get rid of some protons or neutrons to become stable. Before we look at these types of reactions, first you might be wondering, okay, we've got protons, which are positive, and neutrons that don't have charge in this nucleus. What is holding them together? Because protons and protons are both positive, so they should repel one another. And you would be correct in thinking this, except there's this force called the strong force, and it is a force of attraction holding together the nucleus. So a force of attraction between protons and neutrons. In the nucleus. Now back to our reactions of becoming more stable. A radioisotope is another word for the atom that's way too big, the one that's unstable and needs to go through radiation or a nuclear reaction in order to become stable. So our radio, think like radioactive, isotope is a type of atom. So a radioactive ion is an unstable atom with a large nucleus. As a result, we talked about earlier, they're going to try to become stable by getting rid of protons and neutrons and just becoming a little bit smaller. We have 3 different ways that radioisotopes will do this, and that's through alpha, beta, and gamma decay. The process of decaying is called transmutation, changing from an unstable nucleus to a stable nucleus. And in the process, particles of radiation will be released, and that leads us to alpha, beta, and gamma. Changing from an unstable nucleus to a stable nucleus. Sometimes transmutation is also called decay or emission. But all of these terms are referring to an unstable nucleus becoming stable by getting rid of some protons and neutrons in a certain ratio. So we have alpha, beta, and gamma particles symbolized with Greek letters. So alpha kind of looks like a fish, beta is a bee with a tail, and gamma sort of looks like a fish pointing downward or a Y with a loop, whatever helps you visualize it the best. So alpha decay is the release of 2 protons and 2 neutrons from a really, really big nucleus. And if you think about it, 2 protons, that is helium. So this is helium-4 nucleus that is released because the nucleus was way, way too gigantic. And so this is the fastest way for them to get rid of those particles and become neutral. So it's our helium-4 nucleus. It's made of 2 protons and 2 neutrons. And it's nuclear symbol is going to be represented with helium, mass of 4, protons 2. You could also use the alpha symbol instead of helium interchangeably, like you'll see in the example here, but we will look at that in part 2 of this video. While we're looking at particles of radiation, we also want to consider their dangers. So when nuclear reactions occur, this is a release of energy, and so it can be a risk for human health. And so an alpha particle is probably too large to actually go through many materials that would be kind of between us and an alpha particle, but if it was ingested, it could cause radiation poisoning. So we're going to make a list of ways to escape the different particles or the way that they're shielded. I'm going to list out the thinnest material that will be shielding. Anything thicker than what we list obviously will shield it as well. So an alpha particle is shielded or will not be able to pass through things as thin as paper, even our skin or clothing. They can't get through. But like I said, if ingested, then you might face some alpha radiation poisoning, some sickness, that kind of thing from the radiation. Beta decay is the release of an electron, because what happens in beta decay, if you think about this with me, is a neutron, which is neutral in charge, becomes a proton to help shift the amount of neutrons. Too many neutrons, so it changes into a proton by releasing an electron. So let me say that again. Something that's neutral, it spits out a negative charge and now it's positive. And that is beta decay. It releases an electron. Because a neutron turns into a proton. Yes, that is possible in a nuclear reaction. Who would have thought? Kind of cool. And the nuclear symbol for beta is also kind of funky. It is an electron, so it has no mass, as we've talked about before, so that's 0 for its mass number. And beta or electrons aren't on the periodic table, but they have a -1 charge, so our kind of workaround here is to put it as a -1 atomic number, which again doesn't really exist, but we use it for the beta particle to represent it within a reaction, just like written here in a reaction. And the third particle is gamma radiation, and this is the strongest radiation. It does not have an actual particle because this is energy, and it can go through really anything, making it really dangerous. So it is an energy wave, which you see those little arrows, high energy wave, and it is shielded by nothing that is thinner than concrete or lead. So it has to be very protective in order to stop gamma radiation. And then beta is kind of in the middle. So anything that is like wood would protect against beta, or like sheets of metal, those would also protect against beta radiation. And also we talked about how alpha, if ingested, it would affect you. Well, beta and gamma progressively get stronger, and gamma radiation will pass through skin and bones and can actually cause harm and burns without ingestion just by being around it. So it needs that really strong protection. Now, if you will go to page, I don't know why it's doing that. If you will go to the next page, we're going to visit the rest of this in part 2. Here we go. Nuclear apocalypse. Can you escape the radiation? So using what we just talked about with shielding, I want you to read through each of these scenarios and then circle which particles. It can be one or multiple or all three, but none is not one of the answers. for any of these. But read through the scenarios and then circle the particles that apply based on the shielding that we just talked about. So we will get started on this and then you can continue it on your own. It is the end of the world as we know it. Residue from the bombs of World War X linger in the air. Use your understanding of alpha, beta, and gamma radiation to save your family and friends from fatal radiation poisoning. Can you figure out which types of radiation are at the following locations? Circle your answers for each part of the story. At the dawn of the apocalypse, you and your people flee toward a demolished city, but you find no obvious options for shelter. Night falls and you need a quick place to stay, so each of you decide to make cardboard boxes your homes for the night. In the morning, you do not feel any effects of radiation. However, there are particles of radiation still in the air. What particles were blocked by your cardboard homes? Which particle is not able to penetrate and pass through cardboard? Alpha. Think about paper, skin, clothing. Cardboard would be an example of something that thickness. Alpha. Beta and gamma would both be able to pass through that. So I want you to use this same line of reasoning to finish number 2 through 6 on your own. We're going to finish balancing the nuclear reactions and other types of reactions in part 2.